And so we have Brian Brooks from ARM, who is going to talk about the path to getting FIDO, VPP, all of these cool things, working on the ARM hardware architecture, because obviously, supporting multiple hardware architectures, sort of gives us a lot more, ability to address the market. So this is great. So I will just let you run with that.
All right, thank you. Mic check. Yeah, good. Okay. Cool. So my name is Brian Brooks. I'm a software engineer at ARM, and I'm here to share a little bit about running VPP on an ARM-based platform. So what does ARM want to achieve through FIDO? Really, to summarize it, it's first-tier architecture support. So the ability to take VPP, clone it onto ARM-based platform, build it, run it, almost make it boring. It should just work out of the box, like a standard box. And some of the times projects don't necessarily work that way. You'll pull it, clone it, build it, and it might not work. So some recent news is that ARM builds were just integrated into the CI, so you can now get packages for Ubuntu, I believe. If you look at some of the current activities in terms of what's happening with ARM partners and FIDO, there are 4 types of hardware platforms that are being integrated into the upstream lab. Half of them are for CI, so making sure that patches don't actually break when they're compiled on ARM. And the other half are for making CSIT test beds out of them. So we can actually run this awesome CSIT test framework and automation to see how these platforms really perform under a variety of different workloads. And to see a little bit more about what's happening within this community, you can go to the wiki at the bottom. We try to keep meeting minutes and recent patches there. Okay, so in order to understand how VPP runs on ARM, we decided to go with this really small mini ITX platform. It's called the Macchiato bin. You can get it for about $500. Almost everything's open source in terms of software. So the firmware, the kernel, the bootloader, the SDK to access the on-chip interfaces. There's 2 10 gig interfaces that go directly into the chip. So there's no PCIe bus. And we use T-Rex to send traffic into the system, and we run 2 use cases. First one's L2 cross-connect. What this really means is take all the packets that come in on one port and put them out the other port, and vice versa. And then the other use case is IPv4 routing across subnets. So we might want to wonder what path the packet takes through the graph. We know that VPP is graph-based and it has nodes that do the actual packet processing. Well, we can use the tracing facility in VPP to trace a packet to see which nodes are actually process the particular packet that we're interested in. And in this case, when we do an L2 cross-connect, meaning just take a packet in from one port and send it out another port, it'll traverse through at least 5 nodes here: the device input node, Ethernet input node, L2 input node, L2 output node, and device output node. Now that we know what nodes the packet takes, it would help to understand how VPP actually executes the graph. So here we have a pointer to the input node, And what this will do is essentially take packets from the device and enqueue them to the next node. And it'll do that by enqueuing handles to the packets into a frame that's destined for the next node. And then that next node that packets were just enqueued to will be put on a pending list. And then that node, which is sitting on the pending list, will then be executed, and it will probably look at those packets and figure out which node to enqueue them to next via another frame. And you rinse and repeat this process until eventually the packets make it to the end of the graph, where they'll be transmitted out the interface. Buffers will be recycled. And what we can draw from this is that really VPP executes the graph as a breadth-first traversal. And in between each node along the edges of the graph, you have these things called frames, which hold essentially a batch of pointers or handles to the packets. Okay, so now what about the multi-threaded use case? Well, you take all that we just talked about, draw a box around it, shrink it, and then duplicate it. Literally, duplicate it. You can add in a memory subsystem. And in the bottom here, you still have the port. But now you need to duplicate the interfaces to that port. That's also a word that could be used.
Well, when one packet comes in, does it go to every place or one place?
Yeah, so, and then you apply flow to core hashing. So when the packet comes in, you can hash it to one of these interfaces. These yellow queue pairs can be thought of as an interface for a particular CPU to interact with the port. There's also a show run command that's very useful to help you understand how much time nodes might be taking to execute. On the right-hand side, there's clocks. And on ARM-based systems, this represents the ARM generic timer, which is a separate clock from the CPU frequency. It's running at a fixed frequency. And you can find this, there's a couple different ways to find the frequency, but a quick one is just to grep demessage. And here on this system, we see that this clock's running at 25 megahertz. So it's a clock period of 40 nanoseconds. So it's not the same as the CPU frequency. We have. So you can get access to the clock cycle through the PMU counter, but that requires a kernel module to enable user space access to that counter. So. If, yeah, it would be an extra dependency. So one of the things we tried to better understand what affects the performance is changing the batch size. So the default batch size is 256 packets. We tried increasing the batch size and decreasing the batch size to see how that affects the actual throughput. Turns out on this system, a batch size of 128 packets turns out to be optimal. And on the right-hand side here, what these graphs show are the relative execution time of each node, each of those 5 different nodes for this use case, with respect to each other for a given batch size. So the optimal batch size seems to have input and output nodes that are relatively balanced. And the greatest batch size, 1024, which has the worst performance, seems to have unbalanced nodes, execution time of the input and output nodes. So now we want to find out why this may be fast or slow or how this actually performs. So we can use the Linux perf tool. This is a tool that can help you understand where time is being spent in the system. On the right-hand side, we see here a particular hotspot in an Ethernet input node. And it's showing us that roughly 70% of the time is being spent executing these two instructions. What they're doing is they're loading a half word, so 16 bits, from a 12-byte offset from a memory location. In perf, you can use the S key to toggle C source code and assembly, so you can hopefully trace back from assembly to C to get you in the general vicinity of where you should be looking, but depending on the optimization level and whatnot, it can be a little bit tricky to do that at times. In this particular case, what it's actually doing is looking at the Ethernet type of the packet in order to decide what to do next with the packet. So this is the first time that its VPP is actually looking at the packet. So this is VPP, it's supposed to be fast. The reason why this node is slow is because it's looking at the packet. So why is that slow if this is supposed to be fast? Before we try and answer that question, let's just revisit how nodes actually process packets. At the heart of every node might be a dual loop or a quad loop or a single loop. Has anybody heard of single loop, quad loop, dual loop? Okay, some people. Okay. So a dual loop is when you unroll a loop twice and then interleave the body of the loop. And then you add some prefetches. And what prefetches do is they request data from the memory subsystem ahead of time, so that way, hopefully, when you get around to actually touching that data, it's closer to your cache. So it's the overall execution, hopefully, is faster. So if we're unrolling loops and we're prefetching and we're doing all of this optimization, why is it slow? It's even though we're doing all this cool coding for performance, it's still slow because of the memory subsystem. So let's try and figure out what are the latencies to access memory on this particular system. This graph is showing output from LMBench. This is a tool that can be used to measure the latency to memory in your system. And the y-axis is time, the x-axis is size of memory. So if the memory is small, if the memory that you're touching is small and fits into cache, it's going to execute quickly and not take so much time. But as the memory region grows, less and less of it can fit into cache, so it'll take more time. Usually this technique is used to try to understand what are the latencies to the various cache levels in your system, and even going all the way out to main memory. So when an Ethernet packet comes into the system, and you touch it, you look at the Ethernet type of the packet, where is that going to reside in the memory subsystem? Is it going to be in the L1 cache of the CPU? that is actually looking at that packet, or is it going to be all the way out over the DDR bus residing in the RAM chip? And in this particular case, it's in the RAM chip. But is that the best that we can do? Is that the way that systems are designed today? Turns out that it is possible to DMA packet data and have it reside in the cache of the chip. So within the ARM ecosystem, some partners do this their own way. Just recently, support for cache stashing, this ability was standardized in the AMBA specifications. AMBA is a set of specifications for the hardware interfaces between all of the different blocks in the system. So we could sort of expect to see broader support for cache stashing in chips in the future within the ARM ecosystem. So now that we know that we might be dealing with higher memory latencies here, and VPP was written in a way to sort of account for this memory latency, is there anything we can do to be a little bit more aggressive in terms of getting the data to the core, so that way when we look at packet data or any other type of data, it'll be in cache. So by default, VPP will prefetch one loop iteration ahead. What if we just prefetch 2 or 3 or 4? We just prefetch even more ahead in the system. And it turns out we have a table here on the left-hand side. We can get lower execution time in clocks and higher throughput if we be a little bit more aggressive about the prefetching. And this is for a dual loop. Turns out the same or similar sort of performance in terms of throughput and clocks can be achieved with a single loop. And can we do any better? Well, what we're really doing is we're trying to predict the time it takes to load from memory into the L1 of the core. But there are different levels in the memory hierarchy. So is there any way that we can account for those different levels in the memory hierarchy, which may have different memory, different latencies to access between each other? So on ARM, you can separately prefetch into the L1, the L2, and the L3. You can prefetch for load, prefetch for store. And if we split the prefetches into prefetching into the L1 a little bit closer, and then prefetching into L2 even further out ahead, we can tune for those latencies separately. Here's another example of a bottleneck on a Cortex A72 core. The PRFM instructions are prefetch instructions. So if we look at them right here, we have 1, 2, 3, 4, 5, 6, and then on the 7th prefetch instruction, we get a hotspot. Any guesses as to why this might be a hotspot? We got a nod. All right. Yeah? Great question. Okay. So we go and read in the processor manual, and we see something in the L1 memory system is a non-blocking and supports hit under miss. What that means is that the L1 cache can continue to serve hits to other cache lines as long as misses are outstanding. And for normal memory, that's cacheable memory, up to 6 64-byte cache line requests can be outstanding at a time. Okay. So the takeaway here is that when you unroll loops and have aggressive prefetching that can be very demanding. On this slide, we're showing some other hotspots, and these are related to accessing various cache lines, which are parts of other data structures that are involved in simply exchanging data between the CPU core and the I/O device sitting somewhere else in the system. If we take into account the batch size of the number of packets that we're processing, and then you kind of multiply that by the number of cache lines that you're touching, you can roughly get an idea of how much data you're trying to pull into the various levels of caches. So some initial remarks are that most hotspots are memory accesses. Software-defined data placement consumes processing cycles. What this means is that when you do buffer memory management and software, that can take time on the CPU. Unintentionally ordering memory accesses can slow down the system. So there's a case that was semi-recently patched in upstream, but what it was executing is a compare and swap. And what this was doing was not only doing the compare and swap, atomic operation, but it was also using an instruction that orders accesses to memory such that memory accesses cannot be reordered to before or after that instruction. And the compiler may fuse loops which alters memory access pattern from the original program order. So if you write software where you think that memory is going to be touched a certain way or in a certain pattern, it still has to go through the compiler, and that same pattern might not be preserved once the compiler is done with optimizing that particular code. And there are some further directions that we'd like to do, such as understanding the multi-core numbers and multi-core scaling. There are ways to leverage more of the counters in the PMU. Enabling cache stashing on the systems. That way, when the I/O device DMAs packet data into the system, that can actually reside in the cache instead of on main memory. And we also need to see how VPP performs on other platforms. This is a low-cost mini ITX system from one particular vendor. There are a lot of other platforms, or there are some other platforms that would be good to run on as well. So some preliminary results for 64-byte packet size, single flow, single core. Just by tuning, prefetching, and eliminating some of the other hotspots in the system, we can get about a 3.1 to 3.4x speed up for these simple use cases. And on the right-hand side, we see that as the packet size increases, so does the utilization of the link. Yep. Yes. So the green dotted line is the 100% line rate. Oh, yeah. So these are 10 gigabit interfaces. So that would be like 14.4 million packets per second. All right. And since this talk is titled The Path to Fast Data on ARM, I think it helps to be aware that there are a bunch of different disciplines involved in achieving fast data on a particular system. So on the left-hand side, what we have here is the ability to run certain types of workloads and use cases at scale and efficiently. This is where CSIT and the FIDO lab comes in. A lot of recent work that's happening in the ecosystem is around this area in terms of fueling hardware into the FIDO lab and then being able to run CSIT on these ARM-based test beds. And then once we're able to run something, we then need to understand how it runs. Does it run well? Can it run better? And that's where looking into performance analysis and optimization comes in. And then once you understand if there's something to do about it, whether it's a hardware issue or a software issue, you can then work with the respective teams in order to make the situation better, whether that's providing feedback to the team or patching the software yourself, whatever you can do in order to make the situation better. And yeah. So this last slide is kind of the English written version of the previous slide. So that's it. Thanks. Yep. Mm-hmm.
Now you may have found you may hit a situation where, for example, on ARM platform, because of, for example, the prefetches that you can do in one shot, you are beaten by that specific case. While on a different platform, non-ARM, that situation might be just working fine. What I'm going with this is, what are we gonna do? We're gonna wrap code with hashtafs architectures to push this to the boundaries. I mean, eventually there is also maintainability in mind, right?
Yeah. So I wonder if this question is about the trade-off between specialization for performance and general portability. And in that case,
and cross-platform as well, right?
Yes, portability across any platform. I guess that really depends.
What's your view, basically? I was curious to know your view.
Yeah. So I'm neutral. It certainly would take a fair amount of work, although I'm not really aware of anybody trying to do this particular work in VPP to actually scale such a situation across all the graph nodes. So let's say on one particular system you want to prefetch and you have these sort of performance parameters, and they might need to be something different for another system. I don't actually know how much work that would be, but
Let me just comment on this one. So
yeah.
I can see that we do quad loop and dual loop in most of the graph nodes, right? But the problem is that a lot of them are not following the same stride. Depending on the amount of the code there, it can be in some places we are doing, like you explained before, we are prefetching two packets in advance. Somewhere we are doing 4 or even 6 at some places. So each graph node is basically tuned manually, and it will basically mean that for every single different CPU case, you will need to do that manually, right? And it's not only ARM problem. I've noticed the same cache issues on Intel. On Intel C3000 series, which is basically the Denverton. Same thing, basically. I can see that it's falling out of cache and waiting on the memory access. So, okay. I mean, we can start with quad and dual loop, but I'm not sure that we will be able to really do the full optimized pick the right stride for every single CPU kind of approach.
So, are you saying that this is sort of happening anyways for a variety of systems, and we might need to come up with a solution for how it can scale to more?
Well, I'm just saying that we cannot do tuning on the per CPU type basis, right? That's the problem. I mean, last week I spent a significant amount of time on reshuffling the DPTK input node, and it was on Skylake I was getting like significant improvement in performance, and then on the Haswell it was basically drop. So even in that kind of steps, tuning for one can easily mean that you lose some performance on the previous generation.
Okay.
So.
Somehow the theme of the question, like sometimes you have to give up maybe a 0.2% improvement in favor of portability and ease of maintainability for the code, or at least that's my view on it. There was another point that you mentioned. I think I didn't quite get it. You said that basically memory was being reordered when comparing swap instructions was used. You were talking about memory barriers in that case, or what was being done?
Yeah, in this one particular case, it was using the sync built-in.
Sync and fetch or something like that.
Sorry. Sync, compare, and swap, or when it and
add or sub or something like that. No.
Test and set, maybe test and set. But the sync built-ins have an implicit full memory barrier for those.
Yes, so that is another difference between ARM and x86, where x86 is basically unlocking just a cache line. So there's basically no difference between doing atomic or non-atomic. On ARM, it really matters because you are locking the whole bus, right?
It'll keep track of the cache line and try and modify it, but if it's been altered, the state of the cache line has been altered, it'll just retry. It's a more of a load link store conditional pattern, so it won't lock.
Yeah. Do you remember where in the code that was?
The
in
device
L2
and
path.
queue checking for the interrupts pending bit.
But that one is just once per frame. That one should not affect performance. There is another option, possible issue in L2 path where we are, I think, using the atomic for per packet counters or something. Yeah.
Okay.
But the one you are mentioning is really it doesn't hurt. It should not hurt because it happens just once per the full frame of packets.
It was something like.
Yeah.
It was measurable.
Really.
Yeah. I don't remember.
Yeah, I know which one you are, and also that one should work only in interrupt mode, if I remember correctly.
It was a conditional where it was checking for pending or polling.
Yes. So we swapped recently we swapped the conditions, right?
Yep.
Yeah.